Hi everyone! Welcome to the video lesson for Monday, March 15th and Tuesday, March 16th. Today in class we started kind of a new topic, but we're still in Unit 6, all about reactions. Instead of looking at conversions, we started looking at double replacement reactions. We started looking at how we can predict the products of a double replacement reaction and how to determine if a reaction actually took place or not. So we started with a warm-up. We followed up with some notes. There was no new homework assigned tonight that's due. However, there are some practice problems available for you in our module. Today's warm-up was quite a throwback. I gave you 3 different ionic compounds and asked you to give me the ions that made it up and to then balance the formula. Included with the warm-up question, I gave you quite a few resources that you can pull from to remind yourself how to balance formulas and how to look at my ions. I will remind you that the most important resource is your periodic table and common ion chart. They have all of those fixed charges and those Roman numeral charges and the charges of our polyatomic ions there to be looked up. So I start with an example, lithium sulfide. If I look up lithium on my periodic table, it's in group 1. Its symbol is Li. Everyone in group 1 has a +1 charge, so I wrote Li with a plus. Sulfide, well, that ends with "ide." Almost all of my anions that end with "ide" are on the front of the periodic table. If it ends with "ide," it means it don't hide. So sulfide would just be sulfur. Sulfur is in group 16, and everyone in group 16 has a -2 charge. So when I balance this, I use the crisscross rule. The 1 for my lithium becomes my subscript for my sulfur, which we do not write, so it's blank. And the charge of 2 on my sulfur becomes the subscript on my lithium. So I get Li2S. Next, I asked for lead-2 iodide. So if I look for my lead, I can see it has a Roman numeral, so that means it's going to be somewhere in the middle of the table. And it is a little bit to the right. It's underneath the staircase. Since it says lead-2, that gives it a charge of +2. Remember, Roman numerals tell us the charge. I like to think of Roman soldiers charging through Europe. If you're not sure, you can also check the common ion chart. Almost all of the metals that we use with Roman numerals are listed there with their charges and symbols. So lead-2 would be Pb with a +2 charge. Then my iodide, it ends with "ide," so that means it's on the front. If I look at my different elements, iodide looks a lot like iodine. Iodine is in group 17, and they all have a charge of -1. So again, I use my crisscross rule. The 1 from my iodine goes down to my lead, and the 2 from my lead goes to my iodide. So my balanced formula is PbI2. Next up, I have aluminum nitrate. Notice, aluminum does not have Roman numerals, so I look at my first 2 groups and aluminum is not there. If I look in the middle, the Roman numerals area, it's not there either because those all have Roman numerals. Aluminum is right underneath the staircase, the metalloid staircase. If I look up, it's in group 13, and all of those elements have a +3 charge. So my aluminum has a +3 charge. My nitrate, it ends with Ate, and anything that ends with Ate is a polyatomic ion, which means I need to look it up on my common ion chart. So it's NO3 with a -1 charge. So I do my crisscross rule. The 1 from my nitrate comes down to my aluminum, so I have no subscript on aluminum. And the 3 from my aluminum comes down to my nitrate. Now, you have to be careful on how you write it. If I have more than one of my polyatomic, so I want 3 of nitrate, which is my polyatomic, I need to make sure I put my polyatomic ion in parentheses. I don't want NO 33, that would mean 33 oxygens and 1 nitrogen. No, I want nitrate 3 times. And last, I have potassium phosphate. Finally, that rule I told you of when you're looking up elements, start with group 1 and 2, pays off once again. Potassium is K in group 1, so it has a +1 charge. And then phosphate, it ends with ATE, which means it's one of my polyatomic ions. So when I look it up on the right side of the polyatomic chart, I get PO4 with a -3 charge. So my charge of 3 comes down to my K, so I have K3, and my charge of 1 on my potassium comes down to my phosphate, so I don't need to write it. So my balanced formula is K3PO4. Now, double replacement reactions involve a lot of ionic compounds. So if you feel that you would like or that you need more practice, please go to this week's module where you will find a wonderful document that recaps all of the rules for ionic compounds and a practice homework from back in November and the answer key so you can check your answers. Remember, if you have lingering questions, you are always more than welcome to check in on Wednesdays or during our student support sessions. When you go to our Week 7 module, you will also notice a link to generate a copy of our next note packet, Unit 6 Notes, Part 5, Predicting Products. Remember, as soon as your copy is loaded, please click right here on the little folder button and change the folder that it's in. These copy documents are just dumped straight into your G drive, which will make it very hard to find when you need this. So please have a folder in your G drive just for chemistry, and then reorganize it so it's saved in that folder. The first slide in our notes is actually copied straight from our Part 1 notes of Unit 6, where we discuss the 5 different types of chemical reactions. Right now, we are only focusing on double replacement reactions. So I wanted to give you a little reminder of what's going on here. Double replacement reactions are when I have 2 ionic compounds, which are always in solution. I mix them together and they swap their ions. So I get 2 new types of compounds. We like to say they swap their dance partners, but these reactions don't always take place. We're going to have to look up and use a reference sheet to find out whether or not we actually get a reaction. On slide 2, I kind of have a quick preview of everything we're going to do here, everything you need. Whenever you are given a double replacement reaction, you'll be given the 2 reactants and asked for the products and whether or not a reaction took place. So you need to start by writing your products. What I highly suggest you do is you always take those first ions from your reactants. So here A and C, those are your cations. They tend to be metals. And then I swap those anions to make your new products. I'm going to show you a little bit more about how to do this in a few slides. However, reactions don't always take place when I mix 2 different solutions. In order for it to have been considered a reaction, you need to come up with a new product. So one of your products must either form a solid or a gas. Today in class, I had this little image in our flip chart to show you. So if I have 2 solutions, one of potassium phosphate and one of aluminum nitrate, what it looks like is that I have 4 different types of ions floating in solution. So here's my potassium phosphate solution. My ions have disassociated in solution. They are not touching each other. And here's my aluminum nitrate solution. Again, they don't have any chemical bonds anymore. When I put an ion in water, when they dissolve, remember those water molecules come, surround my ions, and rip them apart from one another, one at a time. So, if I have a double replacement reaction, I start with 4 ions that are not bound to anyone or anything. If I take these 2 solutions and dump them into another beaker, If I don't form any new bonds, then all that I've done is mix them up. I would have started with 4 ions that were not touching, that were not bound, and I would end with 4 ions that are not touching, that are not bound. So if this happens, there's not really a reaction here. All I've done is create a mixture. But if some of my ions do come together and make a compound, so let's say these guys find each other and they'd rather be bound to each other than those water molecules of tearing them apart, I will get a solid. I'll get solid precipitates. It'll probably sink down to the bottom of my beaker, or they might really like bonding with each other and flow out of my solution, making a gas. So for a reaction to take place, I actually have to have ions come together and form bonds. So we're going to show you how you can look this up in a chart. On slide 4 of your notes, you have a solubility table. This is what we use to look up states of matter after the reaction. Now, you need to be very careful in how you read this. A lot of students see S and think, oh, that means solid. That is not correct. Look at the very top of this chart. I have a key. I've highlighted it in green. S means soluble. Soluble means it will dissolve in water. So if something is dissolved in water, it is aqueous. It is not solid, it is aqueous. Now there are a few other things here. In my first red box, I have SS. SS stands for slightly soluble. If something is slightly soluble, a little bit of it has dissolved. But more importantly, is that some of it has not dissolved. Some of it may have dissolved into the solution, but we can see that there is still some solid that is left over. So if something is slightly soluble, its state is solid. I stands for insoluble. If something is insoluble, that means it is a solid. It will not dissolve in water. And then soluble in acid means that it can dissolve, but only in acid. In water, it will not dissolve. All of our reactions take place in water. So if something is soluble in acid, it will be solid as your product. And lastly, we have D. D stands for decomposes. If you have a product that decomposes, that means you've made a gas. You're going to have a product that bubbles, producing a new gas. If both products of your reaction are aqueous or soluble, that means you did not create a reaction. All you did was create a new mixture. So in order for it to be a chemical reaction, you need to form new chemical bonds. You can't just mix around 4 different ions. On slide 5, I have my example problem and the 3 steps you need to solve any double replacement reaction problem. So step 1, you need to determine the formulas for your reactants using your periodic table and your common ion chart. You need to look up their ion symbols and their charges. Next, once you know which ions you have, so what 4 ions are you working with, you need to make your new products. I suggest that you rewrite your 2 cations. So in this graphic, I have A and C are my cations. Those are my metals. And then you swap out the anions. So those would be D and B. Those are my negative ions, my nonmetals. I swap those anions between my 2 cations to make new compounds. Once I know what my 2 potential new products are, I then need to determine their physical states by using the solubility table. Are they solid? Are they aqueous? Are they gas? If both compounds come out to be aqueous, then there was no chemical reaction. But if one of them was a solid or a gas, you did have a chemical reaction, and you should go back and balance your reaction. So on slide 6, we went through step number 1, determining the formulas for our reactants using the periodic table and the common ion chart. So potassium would be K with a +1 charge. Phosphate is capital P, capital O, 4 with a -3 charge. So if I use my crisscross rule, I get K3PO4. And then aluminum is Al with a +3 charge. And nitrate is NO3 with a -1 charge. So when I use my crisscross rule, I get Al parentheses NO3 close parentheses 3. And some eagle-eye students might notice these are the same formulas from our warm-up. On the next slide, we continued on to step number 2, which is switching the anions to make your 2 new products. So I first wrote down K plus and Al3+, and then I had blank spaces after my K and after my Al. So out of my pool of 4 potential ions that I can use, I've used the first 2. So I actually went in and I crossed out the font there. So now I only have 2 other ions I can place. I have PO4 and NO3. Well, my PO4 was with my K last time, so if I put it with K this time, then there was no change. So I can't put PO4 with my potassium, so the only place I can put my PO4 is with the aluminum. So that's my only option. And now I've used my PO4, so I cross that out. The only ion I have left to place is my NO3, and the only place I can put that is with my potassium. So I would like to write my positive ions first, and then I can start with either negative anion. I know it can't go with whoever it was with before, so there's only one choice of where you can put it. The reason I like this method is it's a process of elimination. I know things can't be paired together, so it must be paired with someone else. And you keep a running total of who you have and have not written yet. Now that I know what ions are going to make up my new products, I need to balance those formulas. So +1 and -1 means I only need 1 K and 1 NO3. Be careful with the crisscross rule with my aluminum phosphate, because if I crisscross it, it looks like I need 3 aluminums and 3 phosphates, but ionic compounds are ratios. So if my ratio is 3 to 3, the correct answer would just be 1 and 1, so AlPO4. I only need 1 of each of those ions. So now we need to move on to step 3, determining the physical states of these 2 products using my solubility table. So I'm going to need to look up my 2 new products and figure out, are they soluble, aqueous, slightly soluble, insoluble, soluble in acid, which would mean it's a solid, or D, decomposes, which would mean it would make a gas. So my cations are listed vertically and my anions are listed horizontally. So my first one I need to look up is my potassium nitrate. So my potassium is in this blue box. My nitrate is in this green box. Where my potassium and my nitrate meet, I get a capital S. So think for a second, what does S mean? On this chart, S means soluble. So if it is soluble, it means you have an aqueous product. So my potassium nitrate is AQ. It is dissolved in water. So far, I might not actually have a reaction. Next, I have aluminum and phosphate to look up. My aluminum is in this orange box at the very top. My phosphate is this red box, second from the end. Where these two meet, I get a capital A. So take a second, look at the key for the table. What does A mean? A means soluble in acid, but insoluble in water. So if it makes something that's soluble in acid, but insoluble in water, my aluminum phosphate is going to make a solid precipitate. So it gets an S. So I did create something solid, so a reaction did take place. So here in my beaker, what happened is my aluminums and my phosphates came together. They formed a new solid. They formed bonds between them. So they found each other, they made some bonds, and we're going to be able to see that solid precipitate form in our beaker if we were able to do this in person. On the very last slide of your notes, I left you some practice problems. Now, these were not assigned, but you're more than welcome to try these out to see if you do understand this. You will get more practice on Friday in your lab, but I will walk through the first one with you now. So here I have a question. My reaction is lead 2 nitrate and sodium hydroxide. So if I look up lead 2, it's got Roman numerals. That means it's probably somewhere in the middle of the table. Keep looking, it's over to the right side underneath that staircase, and its symbol is Pb. Pb. And its charge must be a +2 since it's a Roman numeral 2. Again, you can double check this by looking on the back of your common ion chart. Any Roman numeral metals will have their charges and symbols written there. Next, I have nitrate. Since it ends with ATE, that means it's going to be on my common ion chart. When I find nitrate on my chart, I can see that its formula is NO3 with a -1 charge. Now I have sodium and hydroxide. So sodium, there's no Roman numerals, so there's a good chance it's in one of those first two groups. And there it is. My symbol for sodium is Na, and it's in group 1, so it has that +1 charge. And lastly, I have hydroxide. Now, hydroxide is a pretty tricky one to find. It ends with IDE, so it should be on the front of my periodic table. This should be an element, but hydroxide is actually one of our polyatomic ions. So hydroxide is actually OH with a -1 charge. So I need to figure out my balanced formulas for my reactants. So let's see, I've got a charge of +2 from my lead and a -1 from my nitrate. So I'm going to need the crisscross rule. I'm going to end up with Pb and no subscript, along with an NO3 in parentheses, because I will need 2 nitrates. And then my second reactant is going to start with my Na. If I use my crisscross, it shows me I only need one of each. So Na and OH. Now I need to come up with my potential products. So my recommendation is take your cations, write those ones first. So out of my pool of 4 potential ions, I have already taken care of half of them. I don't need to worry about placing my lead or my sodium now. So now I'm going to start with my NO3 with a -1 charge. Now if I brought it over here to my lead, well, wait, that's who it paired up with last time. So that can't be right. So I'm going to take my nitrate and I'm going to bring it over here with my sodium. Because I only have those two choices, with the lead or with the sodium. And my nitrate was already with the sodium. I can't have that. I need to make a new match. So now my nitrate has been taken care of. The only ion I have left to place is my hydroxide. And there's only one place I can put my hydroxide. That's with my lead 2. Okay, well, now let me make my new formulas. I have a charge of 2 on my lead, so that 2 will become a subscript for my OH. And my hydroxide has a charge of 1, that will become the subscript for my lead. So lead is just Pb. And then my hydroxide is a polyatomic ion. So my hydroxide is going to need a parentheses with the 2 outside of that parentheses. And then my sodium is going to give a 1 subscript to my nitrate, so I don't need to write anything. And my nitrate has a charge of 1, so it'll bring a 1 down to my sodium. So these two balance out. Remember, your final formula should never ever have charges written in. Okay, now I need to look these up on my solubility chart to see if a reaction takes place or not. Now, let's look up our solubilities on our chart. So here I have lead 2. So here's my lead. So I'm going to highlight this whole row blue. And my lead is bonded to hydroxide, so let me get a red marker. Here's my hydroxide. And I get an I for insoluble. So my lead hydroxide is soluble. So far we do have a reaction since at least one of my products is a solid, but let us continue. Now I'm going to look up my sodium. So sodium, here's my sodium. Highlight this one purple. And then I've got a nitrate, so let me find my nitrate. Here it is. Highlight this one green. And it is soluble. So my sodium nitrate is going to be AQ. So we know a reaction did take place. So the one final thing we need to do is balance our reaction. I can start just about anywhere since there are no oxygens or carbons. So if I notice I have 2 nitrates here, but only 1 nitrate here, well, I need to multiply this by 2. So I give this a coefficient of 2. Now I have equal amounts of nitrate, but oh no, now I have 2 sodiums and only 1 sodium. So I need to fix this. I'm going to give this a coefficient of 2. So now I have 2 sodiums and 2 sodiums, but oh no, this gives me 2 hydroxides. Well, let me go over to hydroxides and oh, look at that. I already have 2 hydroxides. So this is now a balanced reaction. So that's what we went over in class today, plus, if you watch this video, a second example problem. I hope this was helpful for everyone. When I see you guys next on Friday, we're going to be working on a lab with this, using videos and taking data. So until I see you guys again, please stay safe and make good choices.